This figure shows part of the curve C with the equation y equals f of x, where f of x is equal to x cubed minus 13x squared plus 55x minus 75. The curve crosses the x-axis at point P and touches the x-axis at point Q. Part A, show by using the factor theorem that x minus 3 is a factor of f of x. So the factor theorem says that if f of a is equal to 0, then x minus a is a factor. So in this case, if I'm trying to show that x minus 3 is a factor, I want to show that f of 3 is equal to 0. So let's do that. Let's substitute 3 into our function. We'll get 3 cubed minus 13 times 3 squared plus 55 times 3 minus 75. Well, 3 cubed is 27. 13 times 9 is 117. 55 times 3 is 165. Take away the 75. And when we do that, we do get 0. So I can write a little conclusion now saying, therefore, x minus 3 is a factor. And that's part A done. Part B, factorise f of x completely. Well, now I know that x minus 3 is a factor, I can divide my f of x by x minus 3 to work out the other factor, or factors. So, x into x cubed goes x squared times. And now we're going to multiply out. X squared times x is x cubed. And x squared times minus 3 is minus 3x squared. And we'll take that away. The x cubed minus x cubed is 0. The minus 13x squared minus the 3x squared. So we're doing minus 13 plus 3, which is minus 10x squared. And then we repeat the process. X into minus 10x squared goes minus 10 times. Or rather minus 10x times, I should say. Minus 10x times x is minus 10x squared. Minus 10x times the minus 3 is plus 30x. And then we'll take that away. The minus 10x squared minus 10x squared will give 0. The 55x minus 30x is 25x. And then one last time, the x into the 25x goes 25 times. And multiplying out, the 25 times x is 25x. And the 25 times the minus 3 is minus 75. So we know when we take that away at the end here, we will get 0 as we were expecting to get. So that allows me to write f of x as being x minus 3 times x squared minus 10x plus 25. And that quadratic factor will factorise a little bit more to be x minus 5 times x minus 5, which I could write as being x minus 3 times x minus 5 all squared. And that's my answer to part B. Right, let me just clear up a little bit of space here. And then we can finish the rest of the question off. So, we've written f of x in its factorised form. Part C says to write down the x coordinate of point P. Remember, point P was one of the routes where the graph passed through point P. Well, that's going to be when x is equal to 3 because of this. And then we need to work out the x coordinate of point Q, which was where we had a repeated route because the curve went through at point P but touched at point Q. So we had a repeated route at point Q, which is going to be at x equals 5 because of the repeated route at x equals 5. Part D. Find the gradient of the tangent to C at the point P. So we want the gradient of the tangent to the curve at point P. So that's going to look something like this, the tangent to the curve at the point P. What's the gradient of this straight line here? Remember, the tangent just touches the curve, so it will have the same gradient as the curve at point P. Well, to work out the gradient, we can differentiate our function to get the gradient function. So when we differentiate x cubed, we get 3x squared. When we differentiate the 13x squared, we're going to get 26x. When we differentiate the 55x, we get 55. And then when we differentiate the minus 75, because that's a constant, that's going to differentiate to be 0. Right, so that's our gradient function. Now we want to work out the gradient at the points when x, at the point P. Now we know at point P, x is 3. So we're going to substitute 3 into our gradient function. And if we do that, we find that the gradient is 4. So the gradient of this line here, the gradient of the tangent at P is 4. We're then told that there is another point S that also lies on C, and the tangent to the curve at S is parallel to the tangent to the curve at P. Now, I've just worked out the gradient of the tangent to the curve at P. When it says down here, tangent to the curve at P, I've just found that the gradient in that case is 4. And this question is telling me that the tangent to the curve at point S is parallel to this, which means same gradient. So the tangent to the curve at S also has a gradient of 4 because it's parallel. So if I take the gradient function of the curve and make that equal to 4, because I know the gradient is 4 at point S, then I can rearrange this equation And now I can solve it by factorising. Or you can use a quadratic formula if you'd prefer. But I think this is going to be a 51, I'm thinking 17 and 3. So I think that might be right. Let's just double check. The 3x times x is 3x squared. The minus 17 times minus 3 does give the minus 51. And the 3x times minus 3 gives minus 9x. And the minus 17x combined with that, the minus 9 and the minus 17 does give minus 26. So yes, what I've said there is correct. So what we're saying is that if x equals 17 over 3, or if x equals 3, in either of these cases, then the gradient of the curve is 4. Well, when x equals 3, we already knew that the gradient was 4 there because that was the x-coordinate of point P that we already found. So actually, we don't want to give the answer of 3. That's the x-coordinate of point P. This must be the x-coordinate of point S, where the gradient was parallel to what it was when x was 3 at point P. So that's the answer.